All right, let's talk about thermometers. So, thermometers are any type of device used to measure the temperature of something. So, they're mostly going to be based on a property of matter changing with the temperature. So, most of these are going to be based on materials that expand with increasing temperatures. The original thermometers were actually made with mercury. Because mercury was really accurate at expanding as the temperature increased to the markings on our thermometers. Not to say that our current thermometers aren't accurate, but they were really, really good thermometers for being used. However, mercury is a neurotoxin, which means that it affects the brain if it's consumed. And so we needed to stop using those because when you break a thermometer, you end up accidentally inhaling some of that at times. So our modern thermometers now aren't usually mercury, they are made out of alcohol. And so the common thermometer you've probably seen like in a laboratory or something like that, or even maybe when you were a kid with the red bulb and the line in it, that is alcohol. And alcohol is pretty good as far as measuring temperature as well, because it does the same thing. As the temperature increases, the alcohol expands because those alcohol molecules are wanting to get farther away from each other. And so they travel up the tube in the thermometer until they are at an equilibrium, meaning that they're not going to expand any farther because there's no more new energy coming in. And so they'll settle at the temperature reading that we're looking for. So I just want to show you some interesting things that are related to thermometers that we used to use. These are not common anymore, but there's some neat properties that you may find that are related to different parts of your programs. So bimetallic strips used to be used in the controllers for heating systems. The way they work is based on the fact that not all materials expand at the same rate when they're heated. So almost all materials do expand when they heat. There's some exceptions, but pretty much everything when you add heat is going to expand because those molecules are going to start jiggling apart, like I talked about in the kinetic molecular theory video. So they're going to jiggle apart to get away from each other because now they have more energy. But the thing is that not all atoms jiggle the same way. And so in something like a bimetallic strip, where you've got iron on one side and brass on the other, when it gets heated, because they don't heat the same way, they don't expand the same way, the brass is actually going to expand faster and more than the iron will. And so when these two are together in a strip, you heat them up, then the strip is going to bend towards the iron because the brass has actually expanded more. And so this is something to keep in mind if you do some metal work where you're working with two different types of metals. That might actually cause some, effects that you don't want, or you can use them to do some effects that you do want. And so like I said, these were used in older thermostats. They used to make them as a coil, so you can see the coil right here. This coil would expand and contract with the temperature to tip this little mercury vial. Yep, our friend Mercury is back again. To turn the switch on and off. So it would expand when it got warm, and then that would tip the vial to turn the heat off, and then it would contract when it got cooler. That would tip the vial to turn the heat back on. So what do we use now? So today we actually have some different types of thermometers and thermostats, because my guess is that most of you don't use an alcohol-based thermometer to take your temperature. You probably use something a little more like this. So thermometers today are actually based on thermistors. These are temperature sensitive electric resistors. So they have the same sort of, the same sort of property. So they're using electricity to do that sort of expansion, contraction type of thing, but they're still doing the same thing. They're going to measure your temperature based on actual properties, in this case of electricity and electrical resistance, rather than, expanding alcohol. There are also infrared thermometers. So this is one that you would use, for example, if you wanted to find out if there were parts of your house that were leaking heat in the winter. They generally don't look like this for taking your temperature, but you may have actually had your temperature taken with an infrared thermometer at a doctor's office. They're the ones that they just kind of pass over your head, but they don't actually touch you, or they just point at you without touching you. And what this does is it measures the infrared. It is part of the what we call the electromagnetic spectrum, which light is part of, but infrared is heat that is released by humans as well as other objects, and we can actually use our technology to measure that infrared to determine the temperature. So that's kind of cool. We also have thermostats that are a little different. So our thermostats look a little more like this. These guys contain the thermistors as well. So they have the same sort of technology as our thermometers. So they no longer use those bimetallic strips and mercury vials. Okay, so that's information about thermostats and thermometers. So then what are we using on them to actually do the measurements? Well, it depends on where you are. So there's the Fahrenheit scale. Now I'm not going to ask you to know the guy who named it and when he lived. I just wanted to put that in there so you had an idea of how long we've had this scale. This, though, you should be a little more familiar with. Actually, most of us here in the United States are familiar with the idea that 32 degrees Fahrenheit is the freezing point for water. So 32 degrees is when, we start getting things like, oh, it's below 32, it's going to snow in Ohio, possibly. So that's actually what the Fahrenheit scale is based on, is the freezing point of water. They set at 32, and then the boiling point of water they set at 212. So that's the Fahrenheit scale. The thing is that the Fahrenheit scale is only used here in the United States and the associated territories and countries. We're it. Nobody else in the world uses Fahrenheit. In fact, I know people from other countries who get a little panicked when they hear that it's going to be 80 degrees out. And that is because everyone else in the world uses Celsius. So Celsius, the Celsius scale, same idea. It was named after Anders Celsius. The Celsius scale came around about the same time as the Fahrenheit scale. But this one was set so that 0 is the freezing point of water, and scaled it 0 to 100 up to the boiling point. So over here you can see the thermometer, and so you can start to see why people might freak out if they are familiar with the Celsius scale. Because this is the standard temperature scale. It's not the actual metric unit, but this is the standard temperature scale that the rest of the world uses. So if we take a look here at the thermometer, if it's 80 degrees in Fahrenheit, that means it's only about 28 degrees in Celsius. If someone who's familiar with the Celsius scale hears that it's 80 degrees out, that means it's almost to the point of water boiling, which means we would be dead. So it's a little confusing to have these two different scales. In the science world, we use the Celsius scale so that everybody in the world is using the same language. There is one other scale I just wanted to show you because it's kind of, I think it's kind of fun. So the Kelvin scale was named after Lord Kelvin. I know, it's shocking. This one was based on observations of gases under pressure. This is in kelvins rather than degrees. So Fahrenheit and Celsius are both in degrees, but Kelvin is in kelvins. There is an absolute zero here. So again, on the Celsius scale, 0 is the freezing point of water. On the Kelvin scale, absolute 0 is the lowest limit of temperature. It's the lowest you can go on any scale. What happens here at absolute 0 is that molecules would lose all their kinetic energy. So they'd sit absolutely, completely still, nothing at all. As of right now, it hasn't been reached. We've gotten close, but no one has ever reached absolute 0 Kelvin. In fact, theoretically, it shouldn't be possible because everything has a little bit of kinetic energy from things like their electrons. Just to show you where the Celsius scale sits. So the Celsius scale sits here in the Kelvin scale. So 273 Kelvin is the freezing point of water. So that's where 0 degrees Celsius sits. And right here is 100 degrees Celsius. So that is the main part of the Celsius scale. The degrees are the same, so a Kelvin is the same size as a Celsius degree. This is the metric unit, and there's no upper limit to the Kelvin scale. So as you can see, we've been able to measure the hydrogen bomb at an insane number of kelvins. There could be upper temperatures than that. So that's why we have the Kelvin scale. All right, that finishes up thermometers and temperatures. The next lecture we'll pick up talking about heat.